5, which is an algorithm for curve sketching. Basically, this lesson covers everything that we've done in grade 11U and advanced functions in calculus. I'm going to skim over this some of this stuff because you should know how to do it, and it's I think explained well enough in the notes. So the first thing we're going to do is identify the domain, and basically the big three things I have to look out for is when the denominator cannot equal 0. So that usually happens when there's a rational function, a fraction with a numerator and denominator. The denominator can't be set to 0 because it gives us something that's undefined. So that will be one of the situations. The second one would be when we have a root sign. It's called a radicand. The radicand has to be greater than or equal to 0 for even functions. And if you don't know what a radicand is, the radicand is basically the values inside the radical symbol. And the last scenario is when we have a function where the function, the log, we have a logarithm function where the value has to be greater than 0. For x-intercepts and y-intercepts, I'm not going to spend any time on that. I think it's pretty self-explanatory. The only thing I'm going to focus on is this one right over here, where it says that we have where the numerator is irrelevant when we have a rational, because when a cross multiplying is going to cancel off. So again, that's going to be the case right there. For symmetry, all you really have to do for symmetry is take your function, wherever you have an x, replace it with a negative x. Make sure you include brackets, especially if there's exponents. Simplify it and compare it to one of two things. You're going to compare it back to the original function. If it looks like the original function, then it's going to be even and symmetrical about the y-axis. Or can you factor the negative from the function? And if you can do that, it's going to be odd and it's going to be symmetrical about the origin. And the last one we're not going to talk about because it really doesn't apply for us, it applies for really the next unit for periodics. For asymptotes, I'm not going to spend too much time on asymptotes, but it breaks down for vertical asymptote, restriction and domain. Horizontal asymptote, we can figure out the horizontal asymptote by looking at the degree of the numerator and denominator, right, the leading coefficient of the numerator, whatever that's right there. And for the oblique, I'll mention something about the oblique. The oblique is when we have the degree of the numerator greater than that of the denominator, but at least 1. So an example would be x to the exponent 3 on the numerator, x squared on the denominator. We'll have an oblique asymptote, and the way we'll find that is by doing long division or synthetic division. We've done first derivative set equal to 0, and when we do that, we actually get something like this. So critical points. So critical points define when f prime of x equal to 0 or f prime of x is undefined. Then we can use our first derivative test and or our second derivative test, or a combination of, to determine if the critical points are max, min, or neither. Then we'd actually plot them all. The second derivative test, which was the last lesson, talks about concavity and inflection points, points of inflection. I call it IP for short. And basically what we do is we take its double derivative, set equal to 0, and it's going to be equal to 0 or undefined, just like for the critical points. We would use those values to check concavity. We did it in a table in the past, and we would plot them out. For the curve sketching, especially for for this assignment especially, I want a lot of detail. I want to see the dashed lines for the asymptotes. I want to see the x and y intercepts plotted and labeled properly. I want to see the critical points labeled with the values as well, and the inflection points labeled with the value as well. Okay, so let's do an example. For the first example, it's saying that each figure of the graph f of x, f prime of x, and f double prime of x is shown, so we have to identify which one is which. We've had a question like this on a test in the past. In this case here, basically what this is testing us on is, do we understand what happens when we take a derivative of a function? So when we take a derivative of a function, for example, x to the exponent 3, my derivative is going to be 3x squared. So we went down by 1 degree. So that means if we go down by 1 degree, potentially there's one less turning point each time we take a derivative. So keeping that in mind, we look for the most turning points. That'll probably be our parent function. Then derivative function, we just reduce by 1 turning point each time. That's for these types of examples. So if that's the case, we have f of x being our quadratic. when we take a derivative of quadratic, we get f prime of x. It's kind of hard to see the prime bits there. And then this is going to be my f double prime of x. When we take a derivative of a linear, we get a constant. For example B, I'm looking at it, and what I'm going to do is I'm going to count the number of turning points. So the blue line has the most turning points. It has 3. The red has 2. The green has 1. So I know that our parent function, f of x, is going to be our blue line. I know that our red is going to be our f prime of x because it has 1 less turning point. And then our green line is going to be our f double prime of x. Excuse me. For the next question, it says graph f prime of x and f double prime of x, given the graph of f of x. You probably have to write small if you're taking notes. Just I want to show all the calculations, not skip any steps so you can follow along. So the first thing we have to do is figure out how we're going to come up with that equation, because I need the equation of that blue line in order for us to figure out how to take the derivative and graph the next one. So I know that f of x is equal to, well, it's a cubic, so we're going to have an a value, which we have to calculate, and it's going to be a cubic, and then we have bx squared plus cx plus d. Now we have to start solving for all these values, right? Off the get-go, we know that d is equal to 0. So I know that d is equal to 0, which is our y-intercept, right? It's going to be our y-intercept. So I can actually write that down. And we know, so we have f of x is equal to ax to the exponent 3 plus bx squared plus cx. Sorry, I said d is equal to 0. It's equal to 2. I'll get it right sooner or later. Just looking back at the graph. Plus 2. Okay. And now we also know that there's another point on the graph. So we know the other point on the graph is negative 2 and 6. So if I plug that in, I'm going to get, every time I see an x, replace with negative 2. So negative 2 cubed is going to be negative 8. So we have negative 8a. Negative 2 squared is going to be 4. So plus 4b. Minus 2c plus 2. I'm going to bring the 2 to the other side. To simplify, we have 4 is equal to negative 8a plus 4b minus 2c. And it's as much as I can go with that calculation. So I still have too many variables to solve for, so we got to do something different. What I'm going to do is I'm going to take the first derivative of the function. So when I take the first derivative, I get 3ax squared plus 2bx plus c. And I know that f prime of x is equal to 0 when x is equal to 0. That's my first critical point. We can actually see from the graph, so 0 and 2 is my critical point. I know there's another one at negative 2, so I'm going to just deal with this one first. So when x equals 0, and I plug in the x equals 0 back into the equation above, we know that this is going to be equal to 0. That's what we're trying to solve for. That's going to go to 0 when I plug in x equals 0. That's going to go to 0 when x equals 0. Therefore, we know that c is equal to 0. I can take the c equals 0 and plug it back into this equation. And if I do that, I want to do it above, right? So I just take a pen and I'm going to do this. I'm going to sub c equals 0 into, I'm going to call this equation 1 so we know what I'm referring to. I'll put it on the other side. Into 1. So if that's the case, we have 4 is equal to negative 8a plus 4b. Subtract 2 times 0, which is 0. So I'm done. Okay? And I call this equation number 2 because I modified it. And we also know that f prime of x is equal to 0 when we said that x is equal to my second critical point, x equals negative 2. All right, so if I take that into consideration, I have 0 is equal to 3a times negative 2 all squared plus 2b times negative 2 plus our C value, right? This was our C, value. So if I clean this up, we have negative 2 squared is 4 times 3 is 12, 12a, and then negative 4b. And I'm going to call this equation number 3. If I were to put equation number 2 underneath equation number 3, we have 4 is equal to negative 8a plus 4b. Now we have something that looks like we can do elimination with. I'm going to add, because I want to cancel out the b's. 0 plus 4 is 4. 12 plus negative 8 is going to be 4a, which gives us a is equal to 1. So far we have d is equal to 2, c is equal to 0, a is equal to 1. I'm missing the b. So I'm going to sub my a is equal to 1. I'm going to put it back into one of the equations. Doesn't matter which one, but 3 looks the easiest. So when I do that, and I have 0 is equal to 12 times 1, which is 12 minus 4b. Bring the 4b over, divide by 4, and we get b is equal to 3. Awesome. Now we have a, b, c, d. We can actually write our function. So we have f of x is equal to my a value, which is 1. So it's going to be x to the exponent 3, plus my b value, which was 3, x squared, plus my c value, which is 0, which cancels out the term, plus my d value, which is 2. That's the blue function. Next, I got to do my derivative function. I'm going to take the derivative of the f of x. And what I'm going to do is I'm going to factor out, I'm running out of space and putting all the equal signs on one line. I apologize for that. And we're going to have x plus 2. So we know that f prime of x is equal to 0. All right. So that tells me that this here is going to be x equals 0. And this here is going to be x equals negative 2. So I want to plot those. Negative 2 and 0, which if you think about it makes sense because those 2 points line up with my 2 critical points. Now we have to draw the rest of the function. So I can do a table of values or just pick some random values for x, but what I'm going to do is I'm going to pick or use the step pattern concept. We know that the equation of the axis symmetry is between the two x-intercepts, which I'm showing as a green dashed line. And theoretically what we're supposed to do is start at the vertex, which is not known, move over 1, then up by a multiple of 1a, and then multiple of 3a, multiple of 5a, and so on and so forth. So because I can move over 1 to get to the next point, I can do it backwards. I can move from these 0, 0, back 1, and then down 3, because a is 3, 1, 2, 3. So now if I use a step pattern, start at the vertex, move over 1, go up 3. The next one would be 3 times 3, which is 9. So starting at the 0, 0, go over 1, up 9. And we know it's symmetrical. I'm going to fit my curve, best fit. And I'm going to label this as being f prime of x. That's horrible. F prime of x. And I'll do the last one in a different color again. So for the next one, we need our double derivative. So that's going to be 6x plus 6. And that's the easiest form because that's a linear. So I can plot my y-intercept, and you know what? My slope is equal to 6, which is equal to my rise over my run, which is equal to my rise over my run. We never do this, never do negatives like this on a final answer. This is only for slope, right? So I can go down 6, back 1, which makes sense because that's my intercept. I go down 6 and back 1 again. So I got as many points I can fit. I'm going to draw a line of best fit. See how well I do this. I can move that just over a little bit. And I can draw my arrowheads. And I can label this f double prime of x. So there you have it. For the example number 3, they're asking for a bunch of different pieces of information. So there's going to be some calculations involved for each. So in this case here, I'm taking an order, right? The first thing I always try and do is try and find the x-intercepts. So let's do that. So we have x-intercepts. So for the x-intercepts, basically what I'm going to try and do, if possible, is factor out something. So I'm going to try and factor out negative x, and what I get is x squared minus 6x plus 9. And I can use product sum, or I can realize that that's going to be a perfect square. Doesn't make a difference how you do it, but it's a perfect square. And we know that f of x is equal to 0 when x is equal to 0 or x is equal to, in this case here, 3. So those are my two x-intercepts. I can actually start a sketch right now, but I'm going to leave it until I get some more points. So next calculation I'm going to do is my critical points. And my critical points happen when I take the derivative of the parent function. So we get negative 3x squared plus 12x minus 9. And I always try and factor something out to make my life easy. So I'm going to take out negative 3, we get x squared minus 4x plus 3. And I think that can be factored as well using product sum techniques or crisscross. All I know is there's going to be an x and an x. I think that's going to be a negative 1 and negative 3. It doesn't matter which way you put it. And we're going to set it equal to 0 as always. So that's equal to 0 when x is equal to 1 or x is equal to 3. And I'm going to find out those two values. So if I do that, go back to the parent function. So just do a calculation here, negative 4, I hope that's right. No calculator. And the other one, we have negative 27, 54 minus 27. That's equal to 0. So therefore, our second critical point is 3 and 0. And that was critical point. The next thing I'm going to do is do my inflection points. For my inflection points, we need f double prime of x. So go back to my derivative function. It's going to be negative 6x plus 12. I'm going to factor out always something if possible. And we know that f double prime of x is equal to 0 when x is equal to 2. And f of 2 is equal to negative 2. And so that means 2, negative 2 is my inflection point. So my inflection point, we have my critical point, and then I should have done it up here as well. I'll do it now. So I have 0, 0, and 3 and 0 are my intercept points. Okay. Now, I'm going to put it together in a chart. So just bear with me a second. And when you're doing these charts, sometimes if you don't have enough rows or columns, you can always add them on afterwards. What's going on? So there we go. I don't know how many I need. I think I need one for f prime of x. F of x is good. And then what I'm going to do is I'm going to plot, so I'm going to have vertical lines. Stop it. I have vertical lines like here. That's for the labels. That's going to be for x equals 1. That's going to be for x equals 2. That's going to be for x equals 3. I think that's all we need. Again, we can always add more as we're going along developing it. We're going to do our f prime of x. We're going to do our f of x. And I'm going to care what happens around x equals 1, our intercept. Is our intercept? Sorry, first critical point. X equals 2, our inflection point, and x equals 3. So this is our critical point, inflection point, critical point. And I'm not going to do the middle ones because it's kind of tight. So basically what I care about now is what happens when I take, I'm going to highlight this so I can see it, highlight a different color. Let's do blue. So we're looking for f prime. I'll highlight this part over here. All I really care about is the sign of what's happened. So I'm going to take a value less than 1 and plug it into f prime of x, so that baby blue highlight. And all I care about is if it's going to be positive or negative, right? So if I put in something less than 1, i.e. 0, I'm going to have a negative 3 times negative 1, which is positive, times negative 3, it's going to be negative. I don't care what the value is, negative. So what that's telling me is the curve is approaching the critical point from above. And if I were to choose a value between 1 and 2, let's say 1.5, we have a negative times, if I put 1.5 in the first bracket, it's positive, so it's still negative. 1.5 negative, it's going to be positive. That means going away from our critical point. Now, I'm predicting that because it's an inflection point, it's still going to keep on going up. It could go the other way, but I most likely it's going to go up, right? And here we go. So if I pick a value between 2 and 3, let's say 2.5, we have a negative times a positive times a negative. So it's going to be, sorry, what did I say? Negative times a positive times a negative is going to be positive. Yep. And again, it's going to go up, away from the critical point. And if I pick a value greater than 3, when I have a negative times a positive, it's going to be a negative. It's going to go down away from the critical point. So, you know what? I can actually draw the sketch already. Where should I draw it? I'm going to draw it right here in the middle. Okay, and I'm going to do it like this. And I know we have x-intercepts right there and here, so that's going to be my 0, 0. That's going to be my 3 and 0. And using my knowledge, we know that somewhere there's going to be 1, 2, at 1 and negative 4 is my critical point. So my critical point of 1, negative 4. And our inflection point we said was 2 and negative 2. 2, negative 2 is approximately here. So my inflection point of 2, negative 2. And if I fit the curve, we know based on our rules that we're going to come down. We're going to keep on going down until we hit a critical point. We're going to turn. There's my concave up, and it's going to go concave down. It's hitting the x equals 3. We talked about the order. If it's an even order bounces, so it's going to bounce, come right back down. So far looks good. So if we look around the inflection point, we can see that's going up towards inflection point, after inflection point, still going up, so it makes sense, right? And it's okay to have extra columns in your chart. If you don't have enough, sometimes it might present itself as a problem. So again, I'm going to do my x equals 1, my x equals 2, my x equals 3, and this is going to be where x is less than 1. This is where x is greater than 3. And we're going to do the same thing. I'm going to plug in a value into my second derivative function. So I'm going to highlight that so I don't get too confused. It doesn't take much. And it's right up there. It's highlighting green at the top, baby green. And if I take a value less than 1, i.e. 0, and I plug it in there, I'm going to have a negative times a negative, which the value is going to be greater than 0. That's all I care about if it's positive or negative, right? So because it's going to be greater than 0, it's going to be concave up, right? So you use concave up, and the shape is going to look something like that, right? If I plug in a value between 1 and 2, for example, 1.5, it's still a negative times another negative, which is going to be a positive, which is still going to be greater than 0, it's still concave up, and it's all the same. If I plug in a value that's between 2 and 3, it's going to be less than 0. It's going to be concave down, and this looks something like this. And same thing, if I do greater than 0, it's going to, sorry, greater than 3, it's going to be less than 0. That's be concave down. So if I can take that information and transfer it back into my graph, it works out nicely. Example number 4 says use the algorithm to sketch the polynomial function. So it tells me I should get the algorithm so I know what I'm talking about. Just give me a sec. And there it is. So the algorithm is asking for domain and range. So first, okay, so here we go. So for step 1, my domain, I really don't care about the range. I'm not sure why it's in there, but my domain is going to be, where is it? there's really no restrictions on that. So it's going to be x is an element of all real numbers, right? Usually there's a restriction if there's a root sign or if there's a rational. My second thing that I have to calculate is my intercepts. So for my y-intercept, I'm going to let x equal 0. When I let x equal 0, we're going to get 0 and -5. And for my x-intercept, at y equals 0, and what to solve for it. That's going to be kind of hard, right? So we have to use test values. And the test values I'm going to use are going to be b over a. So a is 1, so it's basically b. So it's going to be the plus minus 1 plus minus 5. So based on experience, I'm going to try f minus 1 first. So if I have -1, I plug it into the function, we have -1 to the exponent 4, which is 1. Subtract -1 to the exponent 3 times -4, which is going to be plus 4, which is 5. Subtract 5 is 0. So we know that, therefore, x plus 1 is a factor. So I'm going to use synthetic division. You can use long division if you choose. And we have to keep in mind that we have to use 0 placeholders everywhere that we're missing something, right? So it's 1x to the exponent 4 minus 4x exponent 3 plus 0x squared plus 0x minus 5. Drop the 1. We're going to multiply, right? So it's going to be 1. We're going to subtract. So 1 subtract 1 is going to be -5. We bring the 5 over, -5. Pen stopped working. Subtract again. So 0 subtract -5 is going to be +5. Multiply 5. Subtract -5. Multiply -5. Subtract 0 remainder, which kind of reinforces what we did before, right? So we know that, therefore, f of x is equal to x plus 1. And it's going to be x to the exponent 3 minus 5x to the exponent 2 plus 5x minus 5. Now, again, we can do test values, right? And so we'll test again, right? We do plus or minus 1 and plus or minus 5 again, because a is equal to 1. No more factors, but there's no more factors. I'm just going to say that to save some time and space here. Basically, you go through it and see if f of plus and minus 1 works, plus f of plus and minus 5 works. In this case here, it doesn't. So we have our x-intercept, one of them. We have our, there may be more. It's a cubic, so there's definitely be at least one more. Now we have to find our critical points. For our critical points, we have to take its derivative. So f prime of x is equal to 4x to the exponent 3 minus 12x squared. And as always, factor it out if you can. And f prime of x is equal to 0 when x is equal to 0 or x is equal to 3. We should actually find out, I know that if it's f of 0, it's equal to -5. If it's f of 3, grab my calculator, I get -32. So this is going to be 0, -5, and this here is going to be 3, -32. Okay. And now we're going to do inflection points. So we're out of space, let's go up here. We're going to do our inflection points. Actually, I didn't do the symmetry, but inflection point. If I have space, I'll do it. I didn't do asymptotes we talked about. There's no asymptotes. And so I should have technically done that in there somewhere, right? So sorry about that. maybe I'll put it back in here after. I'll do it afterwards. Inflection point. So we're going to do our double derivative. So f double prime of x is equal to, it's going to be 12x squared minus 24x. And once again, factor out something if I can. So I take out 12x and I'm left with x minus 2. And f prime of double prime of x is equal to 0 when we have x is equal to 0 and x is equal to 2. Now we have a problem because we're seeing that, well, it's not a problem, it's an opportunity, right? We see that and that, they appear twice, right? So I'm just going to highlight this here. So x equals 0 when it's double prime and x equals 0 when it's single prime. So what that tells me then is that this here is going to be inconclusive. So we have to do a little check around it. And this part over here is going to be my inflection point. So it's going to be my inflection point. And if I do put in the calculator, I'm going to get 21. I have to come up with the chart now because I did first or second derivative. So my chart, let's draw this. Let's see, one, so let's do something like this. 1, 2, 3, 4, 5, 8, 1, 2, 3, 4, 5, 6. And a little more. Again, your chart may look slightly different than mine. And what I'm going to do is, oops, draw a line up. And what I'm going to have is I'm going to have my f prime of x. I'm going to have my f of x. I'm going to have my f double prime of x. I'm going to have my graph of f of x. And I have my sketch of f of x. So one of the key values is x is equal to 0. One of the other key values is x equals 2, x equals 3, and x is greater than 3, and x is less than 0. I'll fix the last part, it's pretty messy. So that's a 3, and x is greater than 3. So really, I got to do one more thing here, right? There's really a divide after f of x. So really, there's like a little magic line there if you want as well, right? I'll explain that in a few seconds. So what do we know? Well, we know that f of 0 is a critical point, so that's equal to 0. We know that a second critical point is going to be at 3, so we know that's going to be equal to 0. And we know that at f of x equal, our first critical point is going to be negative 5, and we know the next one's going to be negative 32. Okay, if I were to plug in a value less than 0, i.e. negative 1, into my first derivative function, I'm going to get positive times a negative, which would be a negative, which means my graph is going down towards my first critical point. Okay, if I put in a value between that's greater than 3 as an example, if I put 3, so it's going to be positive, positive, it's going to be positive, and it's going to be moving away from that point over there. If I were to put in a value between 0 and 2, let's say for example 1, do I need to do that? Let's check it out. So if I put in 1, we're going to have 1, so positive, negative, so it means it's still going down. And if I put something between, it's kind of hard to see now, it's going to be messy in here, between 2 and 3, it's going to be a negative, it's still going down. Okay, if I were to go on to the next part, right, what I'm going to do is highlight something. I'm going to highlight this part over here. It's going to go all the way down. and I highlight x. This is going to be down over here, and this will make sense hopefully in a few minutes. Into our value less than 0, which means a negative value, into our double derivative function. When I get a negative times a negative, which is going to be a positive, I can put greater than 0 or positive, right? That tells me it's going to be a concave up, or my graph's going to look something like this. We know my double derivative is equal to 0 there because it's an inflection point, right? And then we also know, sorry, I should put it over here as well. That's my inflection point. Matches up with x equals -2, right? And then, so it's going from inflection point to, now if I choose a value between 0 and 2, let's say 1, I'm going to have a negative, which means I'm going to be concave down. So it looks something like this. And if I go to something between 2 and 3, 2.5 as an example, it's going to be positive and positive, it's going to be positive, and it means it's going to be concave up. And doesn't make a difference, no matter what value I pick after 3, it's going to be the same thing. I don't have enough room for the sketch, but the sketch will look something like that. And you can label all the rest of the stuff for yourself. One last example. I'm gonna go back to this one again, and I didn't do the 2 of the steps, right? I didn't do the symmetry. So in this case here for symmetry, I'll do it in green. If I do step number 3, right, symmetry, I'm basically gonna have f of negative x is equal to basically negative x to the exponent 4 minus 4 times negative x to the exponent 3 minus 5. F of negative x is equal to, that's still x to the exponent 4. That's going to be negative x, so it makes plus 4x to the exponent 3 minus 5, so it's neither. Okay, asymptotes we talked about, and that's it for that part. Once again, I apologize, I should have done it in order, right? And then if I really want to, I can label the rest critical points. I can put no asymptotes, whatever. Example number 5 again. Okay, I'll try not to miss any steps this time. So the first thing I'm going to do is talk about domain. So in this case here, x could be any real number, but x could not equal 1. I really don't care about the range right now. If once I do the graph, I can actually see what the range looks like. But in this case here, it'll be everything except for the oblique asymptote, so I'm not too worried about that. The second thing I do is the x-intercepts. For the x-intercepts, what I'm going to do is I'm going to let y equal 0. And when I do that, denominator really has no impact on a cross multiply. So what's going to happen is I have x squared is equal to 0 or x is equal to 0. So I can graph that. So x-intercept 0, 0. And so I'm putting therefore 0, 0. For the y-intercept, and there's only be 1, right? What I'm going to do is I'm going to let x equal to 0. And when I do that, I get 0 over negative 1, which is basically equal to 0. Therefore, it too is going to be 0, 0, which is already labeled. For symmetry, so what I'm going to do is f of negative x. Wherever I see an x, I'm going to replace with a negative x. I'm going to simplify it as much as possible. And that does not equal f of x, nor does it equal negative f of x. Therefore, no symmetry. About a point or the y axis, right? There could be some other type of symmetry, which we're not testing for at this point. For step 4, we're talking about asymptotes. I'll move that down a little bit, it's kind of squished. And for the vertical asymptote, we know that the denominator cannot equal 0, so x minus 1 cannot equal 0. Therefore, x cannot equal -1, so it's my vertical asymptote. I can plot it on there. X equals, let's say -1, sorry, it's +1. So there it is. That's my vertical asymptote. And if I look at the degree of the numerator, it's 1 greater than that of the denominator. All right, so I got to do my oblique asymptote. So for that, I'm going to just do long division. It's probably easier, maybe quicker. Keep in mind, I got to put all my placeholders. All right, so that goes into x. Multiply, we're going to get x squared plus, sorry, not plus, minus x. Subtract, we're going to get x, bring down to 0, and then it goes into it one time, x minus 1, we get 1 remainder. Okay, therefore, oblique asymptote is y is equal to x plus 1. So let's graph that. There's my plus 1. There it is. All right. Next one's going to be our critical points. So I'll take my first derivative. So what's going to be derivative of the numerator times the denominator minus all over. And I'm going to clean this up. So basically, I can't cancel something out. So that means I have to expand. So it's going to be 2x squared minus 2x minus x squared all over x minus 1 all squared. Simplify a little bit more. And we're going to get x squared minus 2x all over x minus 1. And simplify a little bit more on a factor. We know that f prime of x is equal to 0 when x is equal to 0. Or I might show the calculation. 0 is equal to x minus 2, or in this case here, x is equal to 0, and here x is equal to 2. Clean that up for you. So if I were to do f of 0, we're going to get 0, which we already have. If I were to do f of 2, we're going to get 4. So it means 0, 0, and 2 and 4. So I'm going to plot the 2 and 4 before I forget. 2 and 4, there it is. So now we know that our curve cannot cross a vertical asymptote unless there's a pinhole. And the way a pinhole gets generated is if you cancel something off the numerator from the denominator. That's not the case. So the curve will not cross over. So I'm willing to bet that, well, I'll show you what it's going to look like in a few seconds. Just verify my calculation. So whoopsie. Step number 6 is going to be our inflection point. All right, our inflection point is going to be the second derivative. Sometimes I better move that over. Move that over a little bit, just in case. And I fix this up. So we have f double prime of x, and that's going to be equal to our numerator times denominator all squared minus our numerator times the denominator. It's kind of hard to read, but it says Let's move it over a little more. It's a little bit easier to read, so it's going to be x sort of that minus 1, 2 brackets. And that's going to be all over x minus 1 squared, so then just change it to a 4, right? And here's the magic. You can expand that all. It's a lot of work, right? But I can see that we have an x minus 1 over here that can cancel out, with the x minus 1 over here cancel out, with one of those that can cancel out. So when I do that and simplify it, it makes my life a lot easier, right? And I just have to expand 2x, so it's 2x squared minus 2x minus another 2x is going to be minus 4x plus 2. Subtract our 2 times x squared, so 2x squared. And then 2 negatives make a positive 4x all over, try to be nicer, x minus 1 to exponent 3. Now, once again, we can start cleaning things up. We have 2x squared, subtract 2x squared, negative 4x plus 4x. The only thing we have left is the 2. So we have f double prime of x is equal to 2 over x minus 1 exponent 3. And as always, when I set that to 0, and that's never going to happen. Therefore, there's no inflection points. Come on, no inflection points. And we can do the chart. I'm not going to do the chart. I have no more space, and we have to draw the graph. So if that's the case, if there's no inflection points, and those are my critical points, the only way that's going to be my critical points is on the quadrant 1. If it goes down, hits my critical point, turns, goes back up, and there's no holes or nothing else, there's a vertical asymptote it's not going to cross. It can cross the vertical asymptote, but it's rare that it does. Try and do a better job on the graph there. Okay, and the same thing, it's going to follow the horizontal, the oblique asymptote. Try and do a better job again. Follow the oblique asymptote and go back down, and it looks something like that. And we can actually, when we're doing the chart, we can actually do some test values to actually see if that does cross the asymptote. We can do that limit feature that we did in one of the other lessons to see what the end property looks like, and I'm confident that's going to work. So I think that's it for the lesson. So here's this, the algorithm. I wouldn't worry too much about the range, right? And there's the box setup and the graph. And the most important part is a summary for the whole entire chapter up to curve sketching.